Welcome to our second webinar series, First Steps, New Replacement Part Castings Made from Old Drawings, First Article Non-Conformance Case Studies. This is part 3 of 4 parts. My name is Julia Speaker and I am the lead for the American Metal Casting Consortium's Castings Advanced Systems Technology Integration Team, also known as CAST-IT. This seminar is funded by the Defense Logistics Agency and it has been developed by CAST-IT to assist DLA suppliers in successfully supplying these complex cold start legacy castings. Major parts of webinars 1 and 2, especially part 2 of webinar 2, emphasize that the responsibility for vetting DLA legacy casting technical data packages falls mainly on new awardees. Especially vulnerable to oversights in vetting the TDPs are cold start new awardees. Repeat buys have already been through the TDP compliance check as part of the first article approval process, all of which has been completed. But a cold start has no prior basis. It is truly a cold start. Why does this vulnerability fall upon cold start new awardees? It is not intentional by DLA or the engineering authorities responsible for a legacy casting among the services, but it is the reality. The first reason is the aging process of technical data packages as specifications evolve and are updated without an automatic mechanism to update technical data packages scattered among thousands of weapon systems in all the services. There is a 60-month review of technical data packages specified by DLA to the engineering authorities, but 60 months is a long time, even in the context of legacy casting procurements. Changes in military specifications should be caught, but there are changes on the commercial side of procurement that the engineering authorities would be unlikely to see. An example on the commercial side is a common legacy casting aluminum alloy, A357T6, which is specified on many aircraft legacy castings. Because A357 contains a small amount of beryllium to assist in solidification integrity, but beryllium fumes are known as a human lung carcinogen, it is rarely commercially available. Replacement alloy versions of E357 and F357T6 are a little more difficult to cast with the specified solidification integrity, and it is unlikely that an engineering authority responsible for an A357T6 casting would know about all that and update the alloy in the TDP. Another example is the evolution of paint specifications. Legacy parts originally had legacy paint systems. Now, with the evolution to low VOC paint systems, crossing over paint specifications to current commercially available paints can be difficult. This can be true of sealants and adhesive systems as well. Purchased mil-spec hardware such as rod ends, clevises, and bearings warrant a deeper look as well, as do special installation processes when called for, such as bearing staking or safety wiring of fastener installations. The second reason for TDP vetting responsibility falling on cold start new awardees is the lost documentation phenomenon. Among casting dimensional requirements, especially and for any kind of casting, commercial or military aerospace, new designs or legacy designs, there are exceptions and waivers granted for the unique anomalies on the casting surface that don't find their way into drawing revisions and permanent records in the TDP. So, a cold start new awardee, the first article inspection lab, and even the engineering support activity may be unaware of a dimensional deviation having been acceptable in the past, but undocumented. It becomes a non-conformance on a newly produced legacy casting when it had not been a non-conformance in past buys, months or years ago. As our teammate Keith Sturgill pointed out in his segments in both webinars 1 and 2, a cold start new awardee should assume nothing with regard to undefined dimensions, revised specifications, measurements before or after coatings are applied, commercial availability of specified alloys, definition of critical characteristics, and more. The purpose of these case studies, which are at a high level and brief, is to be specific about situations that have come up in first article inspections in the past and have resulted in non-conformances. The dimensional non-conformances are typically the most difficult to resolve and usually result in the new awardee to resubmit a second first article at the awardee's expense. Our CAST-IT teammate, Mike Gwynn, who specializes in casting design and the manufacturing engineering of casting designs to meet specifications, will summarize several casting non-conformance examples formulated generically, but based on actual DLA legacy casting first article nonconformances.
Thank you, Julia. In the context of first steps to launch a legacy casting from a cold start by an awardee who is commonly now a machine shop, let's take a look at 4 case studies of situations that had a problem and what could have been done to prevent it. Our first case study is a cast ductile iron engine cradle for an Army ground vehicle. The case study issue is which has priority dimensionally, an allowable 2-degree draft per a drawing note, or the plus or minus tolerance on a linear dimension specifically identified on the drawing and affected by draft. And the case study principle we're going to examine is to how to figure out what the allowable tolerance is versus the capability tolerance-wise of the mold cavity process chosen when draft is involved. And we'll also look at another issue that comes up. What about this? A drawing note that says draft to be additive, along with another note less specific about the tolerances involved in a specific dimension unless otherwise specified, dimensional tolerances to be plus or minus some fraction of an inch. So let's begin looking at the details. Well, here we have this engine cradle in an isometric view with a bounding box around it. It's about 24 inches wide, and the area that we're going to be looking at dimensionally from a standpoint of a critical dimension is the width of the cradle underneath the engine. The 2 holes are for engine mounts with an elastomer between the engine and the cradle. And the width between, the width underneath the engine is an important dimension because there are accessories on the engine that we want to be sure that there is clearance. If we look at an isometric view from the bottom, we see that there's a cavity at the bottom for lightweighting, and there's ribbing underneath. You can see also I-beam flanges on the top and bottom along the sides. So one strategy to make this casting would be to have a vertically parted mold to mold out that cavity in the bottom, but the sidewalls created by the I-beam flanges top and bottom create backdraft, and we'd have to have cores along the sides in order to accomplish a vertically parted mold. But there still may be advantages in taking a look at that approach. So let's look at a vertically parted mold with those slab cores to fill in the sides where we have backdraft from those I-beam flange features. And here we have it. We have the casting now oriented with the pocket down below so that we can draw it out of the sand more reliably. The pink line is the parting plane of the mold, and you can see that filled in those pockets that are created by the I-beam flanges top and bottom are the yellow features that you see are slab cores. Those 4 slab cores, because of symmetry, can be formed by just 2 core boxes. So it's a fairly economical way to make the casting because the ability to mold out the bottom pocket has advantages. Well, the dimension that we're interested in is across the bottom there of the view that we're looking at, which is actually the top where the engine sits on the cradle. And the draw length across the that creates the draft that affects that feature is 100 millimeters. So the draft offset for that 2-degree draft along that draw length of 100 millimeters is illustrated here, where we now see the cores. The cores have draft on them as well. And you can see in green the offset that is created by that 2-degree draft over the 100 millimeter draw length. And that's 100 millimeters times the tangent of 2 degrees, or 3.49 millimeters, but it occurs on both sides of the casting. So we have a total wide increase of the casting thickness of almost 7 millimeters as a consequence of draft alone. And that's against 105 millimeters plus or minus 4. In terms of tolerance capability for a casting like this, focusing on air set in the green box with well-designed and well-constructed tooling, we could get plus or minus 3 millimeters for a casting of this size in terms of mold capability, since the dimension is all on one side of the mold, being a basic dimension with no degrees of freedom added to the tolerance capability inside the mold. So now we have, at best, the mold cavity capability dimensionally wise at plus or minus 3 millimeters on top of the draft that has already widened the feature by a total of almost 7 millimeters. So when we look at the resulting 105 feature size, we now see that we're allowed 105 plus or minus 4, which would be 101 to 109 millimeters, but it's likely we're going to wind up with 105 plus the 7 from the draft on each side, and then the plus or minus 3 millimeters of the mold cavity making process capability, or in other words, grand total of 109 on the small side to 115 on the high side. That's not likely to be within the design intent of the engine cradle, where accessories and other clearance issues would be right below where the engine mounts on the cradle. Well, let's look at the other situation where we don't have a specific call out for that 105 dimension, but we do have a note that says draft is to be additive, and then the note that would cover the width of the engine cradle in this case would be unless otherwise specified plus or minus 4 millimeters. So again, we have the same intent. So we have the same situation in terms of the 109 on the thin side to a maximum of 115 millimeters across the top of the engine cradle, right where the engine sits upon it. So what's the designer's intent in this case? Well, when a designer puts draft to be additive as a note on the drawing, that's a structural design intent. The idea there is to make sure that walls which have structural capability as part of their design are not thinned down and lose their ability to carry the load case just because of the way draft was formed. So in this case, we're looking at draft being additive as preferred structurally, but the designer's intent on the overall casting profile would not likely be pleased with the idea of 115 millimeters width right underneath the engine as it sits on the cradle. So our vertical tooling design option has a lot of risk associated with it for first article approval. We can be 95% sure that the 105 plus or minus 4 millimeters will fail. And we can be more than 50% sure that our favorable interpretation, looking at those two notes in our favor for our vertically parted tooling design, that the draft additive is really a structural design issue, and then the just general otherwise specified plus or minus 4 millimeters is not specific to an engine clearance concern, but the engineer wasn't expecting a result that would be plus 11 millimeters on the wide side and plus 3 millimeters on the narrow side of any feature across the design. Well, are there other tooling design options? What about a horizontally parted mold with a traditional core to form the center cavity and the motor mount holes, or horizontally parted with a 3D printed sand core? Let's take a look at that. Well, here's what that option would look like. The 2-degree draft still exists, but it's on a different surface. So we see the parting plane now of the horizontally parted mold cavity above, and then we see a slice through the mold cavity showing the lower half of the cavity and the parting plane in pink. And we now have 52.5 as the half of the dimension of the 105 that was a concern for us before. There would be draft on that surface, but that's not the surface that is of concern. The 100 millimeter draw length created a lot of draft that made that 52.5 on each side quite a lot larger. Well, now we don't have that issue. There's draft on that 52.5, but it's in the other plane. So the draft that does exist is going to be machined off because the 2D drawing calls for the motor mount holes to be spot faced, as we see there in green. Well, what about that 105 plus or minus 4 millimeter dimension now? We don't have draft, but we do have mold assembly degrees of freedom that we've been talking about throughout the Webinar 1 and Webinar 2 series. So what we have then is the top half of the mold closing over that core, now expressed as a yellow figure in our examples. And in the lower example where we have a top view that's been tilted a little bit, you can see the core that forms the motor mount holes now and then forms the inside cavity of the upper part of the engine cradle actually could resist the closing over of the top half of the mold on the bottom. So as a consequence of that close over and the parting plane, we have a coarsening of that 3 millimeter capability of the air set process with good tooling and a mold cavity of this size. So the consequence of that would be that we have 1.3 times that plus or minus 3 millimeter base tolerance capability, or plus or minus 3.9 across the parting line and across that core. And we're allowed 105 plus or minus 4. We don't have any draft involved. And you can see that from our tolerance chart that we got our plus or minus 3 from the air set mold process for a casting this size with well-constructed tooling. So our process is capable, but at 3.9 of the 4 millimeter allowed tolerance, we're close to the edge. So what else could we do? We could do 3D additive manufacturing of that core. There would be no draft. There would be no degrees of freedom in creating a complex core, as we can see here. I'll explain all that's involved, but in the upper view, you can see that in green now, because the 3D printed cores have kind of a greenish gray color compared to normally cores made in sand have kind of got a yellowish buff color. So we could wrap with the 3D printing process, since we have such great dimensional capability, so much geometry capability with the 3D printing process for, for cavities and reentrant angles and all kinds of offsets and geometry inside a core's geometry. We could wrap that 3D printed core around the 105 dimension and eliminate the mold assembly degrees of freedom entirely. And so that's what you see with kind of the center addition to the core's width, is it just basically wrapping around the outside of the casting to eliminate the possibility of the closing of the mold having an effect on that 105 dimension. So with a printed core, we have better tolerance capability. Now we're at plus or minus 2. So at this point now we have 105 plus or minus 4 allowed, and with the printed core wrapping around all of the important features, we have 105 plus or minus 2. So we have tolerance capability now with margin to spare. We have a robust situation, we might say, statistically. Well, one more thought. This is a legacy casting. We can't change the drawing. We can't change the fact that the motor mount holes on the top side of the casting are spot faced. But if it were a new casting design, a little more geometry in a 3D printed core comes essentially at no charge. So why not increase the diameter of the core prints at the bottom interface between the casting and the mold cavity? And that's what I've expressed there in yellow, is the fact that the core print could get wider, and then that wider diameter at that point would essentially make what amounts to a spot face for the motor mount cushions or the motor mount bushings. And with the tolerance capability of plus or minus 2 millimeters, that for an elastomer sitting against that surface is plenty good enough. And if it wasn't, you could take a cup grinder in the foundry finishing process and just kiss those surfaces with a circular cup grinder and make them for sure dead flat. Well, now let's take a look at another case study. This one is an aluminum maintenance excess cover. And the case study issue is missing clarification of the groove feature on the revised 2D drawing. And it's the only drawing in the technical data package. So the drawing that's in the technical data package has a note that's missing on the revised drawing that was on the original drawing, but of course, a cold start new awardee would have no idea that that is missing, as well as the responsible engineering authority that approved that drawing when it was revised didn't notice it either. So here is a drawing with some of the extraneous dimensions removed, and we'll take a close-up at the dimension of the groove in question. So we see here circled that the outer radius of the groove feature and the inner radius are shown as typical, and then the width of the groove all the way around is shown as typical on the original drawing, which we don't have. What we do have in the technical data package is this, which is essentially the same drawing, but whoever did the revision for some other reason, perhaps a change in perhaps the anodizing specification or some other unrelated dimensional issue was the reason for the drawing update. But in the process of making the drawing update, the typical note on those 3 dimensions was accidentally, apparently, left off. But it's the only drawing we have, and as we've talked about, particularly in Keith's part 2 of this webinar series, you know, the technical data package is what it is, and as the cold start new awardee, you are obligated to comply with the TDP without regard to whatever may have been in the TDP in the past. That's not known. So what would be the logical course of action for a cold start new awardee? Well, from the size and scale of the hand-drawn groove, it's obvious that the designer intended for the groove to have a constant width around the perimeter and in the corners. Knowing the purpose of the groove is to seal the cover against the housing, a constant width elastomer seal, like, you know, a big O-ring and just basically rectangularly shaped, would be placed in the groove. So differences in the groove width in the casting might compromise the seal efficiency. So it's obvious that that groove needs to be the same width all around the corners and on all 4 sides of the drawing. But pursuing an engineering change to the drawing through the contract officer to the cognizant engineering authority at the governing DoD site would evaporate the first article production lead time. So for everyone's benefit, proceeding dimensionally with what is obvious seems to be the prudent choice. Well, what actually happened? The first article was conditionally approved, but production couldn't begin until the dimensions of the groove were clarified. Well, you can't clarify the dimensions without a revised drawing. So the choice is, do I wait now as the cold start new awardee, or do I wait later? Well, the cost of lead time is the same, but the cost of preparing a new first article for the Defense Contract Management Agency's approval at the production site is borne by the new awardee. So it's less costly to wait at the outset. Now let's look at case study number 3. It's a cast ductile iron gear carrier for a 4x4 transfer case on a vehicle that's somewhat larger than a Humvee, but of similar size. And the casting is about 16 inches in diameter and about 16 inches tall. And the case study issue is a missing go-no-go gauge drawing for the aggregate spline tooth profile. In other words, a go-no-go gauge that goes down in among the splines completely to verify that the spline geometry is not only the correct diameter, but the tooth profiles are correct. Well, what's different about this one? We just learned from the missing typical dimension that if we just get the drawing and make the go-no-go gauge, that's the right thing to do. But there's a new inspection technology especially helpful for castings. As we've learned, castings are more 3D with more 3D surface anomalies than any other engineered product form, metal or non-metal. And this new dimensional inspection technology is powerful, and it's catching dimensional inspection authorities flat-footed. So here we see a white light scan. Most laser scans, which has been the existing technology, are expensive, very capable, very accurate, but white light scanning has become more and more accurate and is affordable. And comparing scanning to solid models, there's software. This is an example of that software, and this is on a 3D basis comparing a scan to a solid model of a crankshaft. And the software enables overlays of a scanned point cloud on top of a solid model for a quick 3D color-coded inspection result. And even more innovative, what we just saw is a 3D evaluation of dimensions, but unique to this case study is using that same scanned point cloud data concept and the same concept of a pre-existing solid model, but a 2D comparison. So here we see a slice through the spline feature of the gear case, and we see now the gear carrier, and now we see the slice as a 2D slice for comparison with a scanned point cloud. So the same software can compare a slice through the point cloud that matches a 2D view from the drawing. So this is really significant, in my opinion, with respect to legacy parts that have a 2D drawing, because with a 2D drawing, you don't have the 3D aspect of checking dimensions. You're looking always at 2D representations of 3D geometry on the drawing in the 3 views or in special sections or detailed views. So basically, to be able to represent on a 2D basis with the point cloud what you see on the drawing as drawn in 2D is a pretty significant application of this scanning software and the overlay software. So applying this to a legacy casting from a 2D drawing, yes, on gear teeth such as this spline. It was unsure if what was presented in the 2D point cloud versus the model slice was fully understood by the inspection lab. But the inspection lab's objection was the comparison was made with an unapproved solid model, and that's right. However, all solid models for cold starts are unapproved. Only 2D drawings exist. So what would we at Castit recommend? Well, we'd recommend that the inspection lab, seeing the 2D slice comparison of the cloud slice versus the solid model slice, will lay out on the actual first article casting the tip, root, and pitch diameters on that first article casting spline. If those match the 2D drawing, well then the tooth profile is going to be acceptable, and then accept that scan result, which is even better as a result, and approve it. Case study 4, a cast aluminum T38 canopy corner bracket. The case study issue here is that loft is a curvy surface profile that's typical on aircraft. It's difficult to visualize in 3D and difficult to express in 2D drawings. So there's a picture of the corner casting that goes onto the corner of the canopies that you see lifted up there on the T38 jet above. And you can see that in the 2 views, top and bottom of the corner casting, that the loft is on the 3D basis. All 3 planes have curvature. A machine shop was the initial cold start awardee, and the part seemed simple, not knowing the complexity of 3D loft. So to procure the casting and drill 4 canopy attachment holes seemed like a no-brainer, and there were 50 castings needed, which was unusual for a legacy DLA casting procurement. Well, there's loft data problems on that 2D drawing. The corner bracket has loft in 3 planes, which is common on aircraft surface profiles, but that is difficult to represent on a 2D drawing. So the draftsman had some incorrect individual data point positions, and it's difficult to detect that that data may be incorrect unless you're familiar with loft on 2D drawings. The machine shop, unaware of possible profile errors in individual 2D drawing loft data points, built a solid model, procured an investment casting, built a machining fixture, drilled the 4 clearance holes, submitted the first article, and it was rejected. They came back and tweaked the solid model based on the rejection and some of the dimensional feedback that they got. They resubmitted at the machine shop's own expense, which is the problem if you missed the first article. As we've been talking in these 2 webinar series, that it's really important to get the first article correct, because that second one, as the cold start new awardee, is on your nickel. Well, it was rejected again. So what was DLA's situation? The 50-piece requirement being unusually large for a legacy casting requirement, the Air Force had T-38 aircraft in need of the brackets. So DLA came to Castit for assistance. You guys know Gary Burrow now, our mold cavity tooling builder expert, undertook a new contract for the 50 pieces. The significance of this case study is that Gary did what he professed in webinar 1 and part 1 of this webinar 2 series. So let's follow what Gary actually did. Well, the cold start H.A. Burrow pattern story. Gary is the 4th generation pattern maker. Now we call mold cavity tooling builder because we do so much important mold cavity building with additive manufacturing technology. So pattern making really doesn't describe what someone like Gary does. So he's the fourth generation of the H.A. Burrow pattern organization. Originated in Southern California, serving metal casters in the aerospace, military, and commercial business sectors. Now Gary's located in Montana. A separate business, not a metal caster, serves all kinds of alloys and all kinds of mold cavity types. A separate business, not a machine shop. Chooses machine shops on the basis of casting machining expertise and machine tool types. For decades, Burrow Pattern has built casting tooling for aerospace loft profiles such as this, and still builds tooling for a wide range of alloys and mold cavity making processes, production castings, commercial legacy castings like critical structural castings for rides in the original California Disneyland Park, and of course DLA legacy castings like this one. As our Cast It webinars 1 and 2 have been professing, it's a mold cavity tooling builder that has the technical expertise that is the foundation of a successful first article launch. Builds the 3 levels of solid models necessary to replicate the original 2D drawing and build all the tooling. Estimates the pattern maker's contraction, which is fundamental to dimensional compliance, and has access to additive and subtractive manufacturing technologies to build tooling and build more accurate mold cavity elements. Specifically, Gary built the first solid model replicating the 2D drawing, making judgment calls on apparently erroneous loft data points and correcting them based on what he could surmise about the erroneous data points. Then the first solid model, which has no pattern maker's contraction rate built into it and no attachments for the mold filling process, Gary used that first solid model to create what we call naked solid model to print a SLA quick cast 3D pattern of the part, not to make a casting, but to check the 3D lofted surfaces as he had created the 3D model from the 2D data. Since the first solid model had Gary's assumed correction to specific loft data points, those corrections would show up on the SLA pattern as consistent with the surrounding loft or still in error with little peaks and valleys in the profile. So based on CMM, visual, and tactile evaluation of the SLA pattern's 3D loft profile, Gary adjusted the first solid model for loft corrections. Then, in consultation with an investment casting shop, built the second solid model with pattern maker's contraction added for the 356 specified aluminum alloy. No additional contraction rate was added for wax, since the patterns for the investment process would be made from direct printed SLA quick cast. And then added the contact geometry for the investment tree. Gary had another separate business, an additive manufacturing 3D printing source, print a few SLA quick cast patterns for casting prototypes and hopefully a first article casting. The SLA patterns were given to the investment shop and prototypes were cast. CMM checks verified that the second solid model with the pattern maker's contraction added was correct, and a first article unmachined casting was prepared. At this point, having finalized the mold cavity making process, Gary would ordinarily build the third solid model, remove the pattern maker's contraction, add the markers from process interface geometry, the gating, risering, and venting contact areas that will appear on the surface of the actual first article casting after those have been cut off and ground down flush and media blasted. So those would be the in-gate contacts, the riser contacts, and the vent contacts in the normal processes. In this case, it would be the contact for an investment casting of the investment tree. And that would enable the machine shop to build the machining fixture knowing about those surface anomalies because they would show up on the solid model. Well, since some of Gary's machine shop partners are in other states, the third solid model is critical in communicating what the actual as-cast surfaces will look like. And here we see what we're always talking about through this entire series of part 1 and part 2. You have to be careful, if you're a machine shop, of these surface anomalies that come from the mold cavity making process. Investment castings are not perfect either. Even with pattern maker's contraction, you can have dimensions that aren't centered, even though it's a highly accurate process, but the metal has to get into the mold cavity somehow. And what you see with the red arrows, and you can see even more so with the shadow of the lighting of the casting when the picture was taken, there's a raised area about a 1 millimeter high of the investment tree contact on that casting, which was cut off with a bandsaw, then lightly ground to be near the casting surface, but a little higher, and then media blasted. So in this case, then, the machine shop was a local Montana source, and here's what Gary and that source discussed: the machining fixture design and targeting. Well, what does that bump mean in machining fixture design? You can't target against an area in which a process interface marker like the investment tree contact would exist, because that bump is going to be a millimeter, as it shows in this particular case, has some width, probably the total width of that bump at varying elevations is about an inch, maybe just a little over. Well, the next casting might have a bump that's only a 0.5 millimeter high, and then the one after that might have then a bump that is 1.5 millimeters high. So if you target against that surface, not knowing that it's there, then the 4 holes are going to vary in hole position and be rejectable, because you can't stand, a 0.5 millimeter, millimeter and a half difference from casting to casting on hole position. So knowing that those bumps are there is really critical to the design of the machining fixture when machining castings. So what happened? The investment shop completed preparation of the first article casting and was given to the machine shop, who set up on the casting aware of the investment tree contact area, targeted elsewhere, and actually clamped against it, which is okay. It's okay to clamp against a process interface marker, just don't target against it. And then drilled the 4 clearance holes, which were very consistent from casting to casting. The machine first article was submitted and approved the first time. 50 castings were produced and used with no complaints. So that's what these principles that we have been discussing throughout the Webinar 1 and Webinar 2 series look like in case studies. So now back to Julia, who will set up the chat box and set up for your questions and comments.
All right, so good morning, everyone, and thank you for joining us for part 3 of our First Steps webinar series. As Mike said, my name is Julia, and I'm the Cast It team lead. So just wanted to quickly give everyone a reminder of who Cast It is and what we do. So we are a team of application engineers, and we work to solve both technical and procurement issues regarding casting. So if you look in the handout section, there are a couple handouts that just go a little bit more into what we do and how we might be able to help you. So I'll go ahead and introduce the team. So we have Dave Powlite, who is the VP of Technology at Steel Founders Society of America. We have Mike Gwynn, who is our casting design expert. Keith Sturgill is a metallurgical engineer who's an expert in all things DLA and government processes. And then unable to be here today, but still important members of our team are Gary Burrow, who is a 5th generation pattern maker and really an all-around casting guru, and Dick Tiana, who's an expert in 3D data. So let's take a look and see what questions we have. So we have one question that says, how do I know that I have a cold start? So I think, Mike, do you want to take a shot at answering that?
I think Keith is probably the expert on that. He sees them all the time. You want to comment, Keith?
Well, why don't you give it a start, Mike, and I'll come in and support you in the end.
Well, the essence of a cold start is that all of that documentation, which basically is the manufacturing engineering history of the prior supplier, is lost. Usually the tooling is, you can't find the tooling. The original documentation of how they made that casting is usually proprietary among the prior suppliers. They're not willing to generally put that into a technical data package. They, making castings from the manufacturing engineering standpoint is a secret sauce, really, of much of the success of making castings that meet all the specifications. So the trail is cold at best and is a vacuum at worst. So you really are starting with the entire manufacturing engineering process and building the tooling and making all of the partnerships and so on with what it takes to make a casting and get it first article approved from a cold, dead cold start.
I don't think I could really add too much to that other than just kind of re-emphasizing that if you haven't been making a part, if you're a machine shop and you're going to bid and you haven't made this part before, there's just a lot to be able to discover in terms of how to make the part, the manufacturing engineering involved, and the tooling involved especially. So just cautionary, be especially careful to go through the tech data package very thoroughly and try to understand what you're building and how this item functions in service. Try to understand that.
And I would say one other thing, Keith, that you emphasized in part 2 is if you are a machine shop, which is 70% of the time you are, choose your partners wisely.
Good point.
All right, great advice. All right, so it looks like we have another question. What do I do if my first article is erroneously rejected based on all the facts available? So Keith, do you want to start off with that one, and maybe we get some input from Mike and Dave?
Well, if you believe your first article was erroneously rejected, perhaps you believe it was a minor non-conformance that should have been a conditional acceptance, and where the minor non-conformance is corrected and verified as corrected by the DCMA at the manufacturing plant. If you believe that to be the case, or you believe that the inspection lab has misinterpreted a drawing or a dimension, the first thing I would do is I would have a conversation with the administrative contracting officer in your region where your manufacturing plant is, and discuss this with the administrative contracting officer, which is a DCMA person, and then you would submit a post-award referral, which would then be flowed to the contracting officer, procurement contracting officer at the supply center, and then coordinated with the product specialist there for that item, and perhaps a 339 would be submitted, request for engineering information to the engineering support activity. But this is the process to, as slow as it might be and frustrating at times, this is the correct process. And if you must go through the proper channels there with the administrative contracting officer, the procurement contracting officer, and the product specialist.
Keith, would you also suggest that you could go direct back to the contracting officer? For instance, if it's a DLA procurement, if you're not able to get a response from DCMA?
Yeah, I have seen that. I have seen that done quite often, and it seems to be an acceptable process. I think it's always a good idea, though, to have the DCMA administrative contracting officer in the loop.
Sure.
But yeah, your point is right.
Or at least keep them appraised too, since they would be watching the lead times and so forth. What do you think with the procurement technical assistance centers, the PTACs that are also part of the DLA? Would they potentially be a resource that people could reach out to?
I think that is true as well, especially maybe early in the process of just trying to discern what the true situation is, you know, do you really have a conforming part or not? The PTAC could assist with that. But when it comes to formally asking for a resolution, you know, going through the contracting officers is the right way to go.
All right, thanks, Keith. All right, so it looks like we do have another question or a bit of comment. Could we review a little bit about the point about risk in proceeding to first article before obtaining clarification on important questions? Mike, maybe if you want to take this one.
Is that essentially the same, Keith, question that you just addressed? You know, what do you do if you have a concern about a non-conformance that you believe is incorrect? Is that the question, Julia?
Yeah, I believe so. Just maybe a little more emphasis on why it's important to get that clarification before proceeding.
I think the one thing that I would preface what Keith has already said is do a careful analysis as the awardee with your partners about the fact, just as we saw in case study 1, are we really correct in the way we're interpreting the effect of draft on a dimension that's been called out specifically with a width that's important functionally or structurally to the part? Just be sure you understand what it is that you have done with your process with regard to the specification to assure that your question about non-conformance is correct.
All right, thanks, Mike. All right, and then how does scanning a point cloud work?
Well, that's a really good question. It's advancing rapidly, and the example we cited using a 2D slice of a point cloud is really innovative. And I have hopes, as does our whole team, that this idea will be picked up on and will help the legacy casting approval process with respect to 2D cross sections in reference to the 2D views in the drawing. But here's the interesting thing. You know, the original scanning technology was based on laser light, which is extremely accurate and usually mounted on a tripod. But this white light scanning now has handheld, quite accurate scanning capability. And here's interestingly what happens. Inside the scanning hardware is software that knits together the scans of many, many attempts to get a complete scan of a casting, let's say, because you're gonna have to pick it up, turn it over, and scan the bottom side and scan views of it or orientations of it that aren't handy. Well, the software inside the scanner knits together the points that form that cloud of data around the surface of that representation very accurately. So you can scan over and over again with a handheld white light scanner, which is a lot more affordable, and get generally a knit together 3D picture of the surface that is accurate enough for the kinds of applications that we have in legacy casting applications. So it's moving rapidly and really powerful for casting.
I'll add one quick point to that. Mike is recently up at a foundry, and they're using that same scanning technology as a way of offsetting some of the traditional setting up with datums and doing CMM touch probe inspection, just because with that scan, it allows you to really see how it fits the GD&T envelope, and potentially if you shift the part a little bit, when you do your final machining, you can end up with a good casting instead of just setting on the fixed datum targets for the inspection. So it's a really powerful tool. One of the AMC research projects actually is looking at using that same technology to digitally interrogate the surface finish of a casting likewise.
Well, those are good points, Dave. Thank you.
All right, great input, guys. All right, and then it looks like the last question, this one's probably for Mike. Mike, that casting tolerance kind of graph picture, how would our attendees be able to access that? And then could you maybe talk a little bit about how it's intended to be used?
Well, it was intended to be used just as we saw in the case study that we looked at. what we could do in part 2, Keith's part 2, we had a little segment on, you know, how that matrix was actually conceived and how it works with respect to the tolerance capability over a spectrum of all the casting processes, as well as the spectrum of casting sizes and how the tooling was constructed, and all that are all factors. So what we could do, Julia, if it's all right with you, is I could extract that segment from Keith's webinar, create a little video along with an image of that chart as we were using it in our example. And then if someone would like to have that, they could give them your email, their email address and their name, and you could then send that extracted video and the hard copy or the image of the matrix as it's used in final form to anyone that would like to have it.
Sure. Yeah, that sounds like it would be something great to refer back to. All right. So it looks like that is it for our questions. So I do want to thank everyone just once again for participating in our First Steps webinar part 3. So I'll say this every time, we really do greatly value your feedback, and we do use it as we develop other webinars. So if you could fill out the survey, that'll pop up immediately following the webinar. It'll also be in your kind of end email, if you will. That would be great. And then also, just wanted to give everyone a reminder that part 4 will be held on November 9th. So that is not next week, but the following week. And there will be information on how to register for that in your follow-up email as well. And then the last thing I'll mention is I'm planning to post the videos for parts 1 through 3 this week. So I'll make sure that's sent out to anyone who registered. So if you missed one of the parts or missed maybe a little bit of the beginning or end of a part, you can catch that. And part 4, I'll post the recording after we have the live webinar, of course. All right, so if there are any questions about the content covered or resources provided, feel free to reach out to me. And if not, then have a great day, everyone.